Okay, this video is going to focus exclusively on graphs and how to translate graphs. In the next part of, remember we're on CVPM, constant velocity particle model, we are going to be given, let's say, a distance time graph of someone running down the hall. And let's say that this graph looks something like distance time. They run that way, they run that way, like that. And we want to translate this motion into a velocity time graph. Draw that over here. Velocity time. We're going to take this segment by segment and think about what's happening. Let's label our segments A, B, and C. C is the entire segment that has this large slope. Okay, when time begins, the person starts running in the negative direction. Negative direction, this is a constant velocity, but you're moving in the negative direction. So I'm going to express this with a negative velocity. That's A. Then the person comes to rest. They stay at the same distance as time progresses. They're not moving, so their velocity is 0. And then finally they move in the positive direction here at, during segment C. Notice that it's moving faster, or they're moving faster than segment A because there's a steeper slope. So I'm going to express that by drawing a line that's way above the x-axis compared to A. And that would be it. We just translated from distance time to velocity time. Okay, can we go the opposite way? Now we have a car that's driving down the street, and we know the velocity time. Velocity time. Let's say it looks something like this. A, B, C, and we want to convert this into a distance time graph. Distance time. Okay. Can we put this into words first? The car is, when time starts, it's moving in the positive direction with positive velocity. Then the car speeds up and starts moving in the same direction but faster, and then the car comes to rest. Okay. So it should look something like this. Time goes on and the car is moving forward. Then the car starts moving faster. How do we express that on distance time? Well, that's a higher slope, a steeper slope. That's B. And then finally, the car stops altogether and is not changing positions. That is C. And that's how we would translate from velocity time to distance time. You should be able to take a graph in either distance time or velocity time and translate into the other. The last standard for CVPM is taking a velocity time graph and figuring out exactly how much distance is traveled in a given time. So in this context, I have a biker. Let's say 10, 20, 5, 10, 15, 5, 10, 15, 20, 25. Okay, this is in meters per second. Oh my goodness. This is in seconds. Let's say instead of a biker, this is a car. That would make a little bit more sense. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so I want to figure out how far the car has gone on the straight path after, let's say, 8 seconds. To do this, I need to take the area underneath the velocity time graph to get the distance. So first I'm going to box it all in. I've got this area. Remember, I'm going to 8 seconds. So 1, 2, 3, 4, 5, 6, 7, 8. And then I also want this area up to 8 seconds. Now let's find the area in these two boxes. First one, the length here is 5. The width here is 20. So this is 5 times 20, which is 100. Distance is measured in meters. And then this box here, which is 1, 2, 3 units long, 5 units high. Remember, we're looking at the y-axis here to figure that out. 3 times 5 is 15 meters. Now we can just add these together. So total distance traveled by the car is going to be 100 meters plus 15 meters, which is 115 meters. We are done with CVPM.